Hello and welcome. I'm Martin Kronbichler. I am the coordinator of the Center of Excellence D2X or DDX. I mean, we have different names, different pronunciations, so don't feel bad if you don't know how to pronounce it. Whatever you do is right. So our Center of Excellence is in a different area, or at least slightly, because we don't work in environmental sciences as HiDALGO2, but we're working towards the human body. And so I want to show you a few insights into our theory and just techniques that we will apply. So this is kind of my outline. I will just show you a few things with the Center of Excellence and then some algorithmic parts, but relatively high level, but just to show you where we are going. So this is kind of the motivating slide. So we are trying to make exascale computations available to the simulation of organs in the human body, where we are using mathematical modeling. Our Center of Excellence is spanning over 4 countries, Germany, Italy, France and Belgium, where we are quite heavy on mathematics. So we are, what I learned today now, we are less kind of developed towards kind of the public sector, even though you could assume that we are in medicine, but we're not there yet. We hope to go there, but I really learned a lot from the interaction. So this is very nice. So we are kind of working on the simulation of organs. I mean, I have 2 pictures here, or 3, depending on how you see it. One is the human lung, where you see that we're essentially resolving the airways of the lung up to a certain structure, which is kind of the red parts here. Then of course there is this gray part, which is not empty. I mean, it's kind of the lower structure where actually the things are going on. So we're actually working on both the fluid dynamics in this red part, which is reasonably big, but the bigger size even is kind of the structural modeling, which is on boromechanical models. And the other picture you see some blood vessel and the heart, and I will come into that a bit more. In our Center of Excellence, I told you we're quite heavy on mathematics, so essentially we're doing a lot of finite element modeling and method development, a bit similar to the Alberta code, but we're using a different discretization method, but it's close in some sense that we're doing PDEs. The name from our Center of Excellence comes from a finite element library, which is called deal.II, which is very much focused on providing toolboxes, but it's not implementing equations. The equations are what we place at the top here, where I just say lung solver, heart solver, brain solver, liver solver, which are our 4 main areas in the Center of Excellence. We have a 5th one, which is more spanning different cell processes, which I didn't list here. So you see that we have this kind of at the top here, then we have this kind of finite element infrastructure, the deal.II in the middle, which I will touch on one more slide. And then we of course have, since we're solving PDEs, we're going to have linear solvers, linear algebra aspects, which is kind of on this other parts here, where 2 of them are developed within the Center of Excellence, which I highlighted in orange, whereas there's 2 more, which is kind of generic software from outside of the EU, you could say. In any case, this is where we're going. Now just quickly on the deal.II library, I don't want to go too much into it, I just want to mention that this is a mathematical project where we want to kind of support any finite element code, not just biomechanics. The name comes from differential equations analysis library, but this is so old that it actually predates my entering in the research. I mean, it's coming from the early 1990s. I did certainly other things at that time. It's a quite mature project in the sense that we have a lot of code. It's not super large, but it's very much focused onto the mathematical framework, so we consider it big enough that it takes some time to support. We are pretty proud of our documentation tutorials. I mean, we have a lot of users attracted because they like the documentation, and just, of course, always from the shell perspective that we were discussing before today, from the perspective that you are a mathematician or engineer who likes the simulation, but still we are quite good in that documentation part. But we are, of course, expanding it in the Center of Excellence towards the industrial users, so we can learn a lot from what you've been doing. Just quickly, don't bother too much about the long text on this slide. I'm just mentioning that we're trying to optimize our algorithms towards the hardware architecture, I mean, in our case, finite element methods, where we essentially started from an approach of performance modeling. We analyzed what is the classical algorithm, which would be these blue lines that you see on the graphs here, which essentially just increase in work when we increase the order. Now the order is something how accurate the methods are working. even though human body has uncertainty, I mean, we still see benefits from going from the left at 1 to maybe 3 or 4, but you see that the classical algorithms have been increasing in cost, whereas our alternatives, which are called matrix-free, where essentially you don't build the matrices because they are memory heavy, we can just gain this kind of memory intensity, and then we gain performance eventually. Again, this is mostly done because we are knowing where we want to go. We've been tuning this in our Center of Excellence. I mean, I'm just showing here 2 slides. And I always want to make the case we do support GPUs and we do tuning on it. So GPU will be the green line here on this graph. On the x-axis, you see the problem sizes, and typically you work somewhere around here on one of the GPUs. And of course, we scale it to more GPUs. But what I always want to highlight is that if you look at CPUs, this is an AMD CPU, which is a similar power consumption more or less. I don't really think that CPUs are much worse. I mean, that's actually, everyone likes GPUs, but we're not exclusively doing GPUs because we know that there is circumstances where CPUs work well as well. Again, always depending on where we want to be. Just showing, of course, if we have very large problems per node, then you see that the GPU is, of course, a factor of 4 faster because it has more memory bandwidth. But there is many cases where we are actually able to utilize CPUs really well. A bit more to application before I stop. This is one of our groups in Italy at the Politecnico di Milano working on hard modeling, where we are developing kind of a whole chain of solution components. So we're doing the electrophysiology, which is the signals starting from the heart when we initiate the heartbeat, then eventually contraction of the material, and eventually the blood pumping out of the heart. So there is a lot of simulations done in that group, not just one, different models, so you need a lot of flexibility in the model. And I just want to show you here this from scalability results. You see that the blue line was the solver that they used at the start of the Center of Excellence. You see the red and the orange line, kind of the new solvers that they developed with our support in the COE from the mathematical part, that you see that from a solver which did reasonably, they got really pretty much improved here. And again, it's related to this matrix-free algorithms, but there's not just that. I mean, there's a few more improvements that they did. And what more I want to show you here is, since we're solving systems, we often work with multi-bit methods. Of course, there is algebraic multi-bit as an established tool, many applications, and we have one of the BSC toolkit development team as well. But we often see that algebraic multi-bit, which would be the top 2 lines, are actually performing worse than if we do geometric multi-bit, if we know about the geometry. And we've been working on agglomeration techniques, working in parallel, working on big scale, unstructured meshes, where we can accelerate these solvers, and it's pretty appreciated if you can reduce this by a factor of 2, because often in many simulations we are time dependent, so we're actually having problems to saturate big machines. If we can reduce the iteration count, we reduce the time to solution, which is important to deliver our results. And of course I could tell a lot more, but I really don't want to waste too much of your time because you're not biomechanical researchers. But I hope I gave you some insight of what we're doing, and in our Center of Excellence we're always happy to collaborate and learn from your experiences, maybe give on some of our experiences to you. Thank you very much.